So in this lecture, we'll be looking at the organic halides. So this is where we have an halide directly attached to a carbon. The halide itself is more electronegative, a lot more electronegative than carbon, which results in this quite polar due to the inductive effects. So we end up with an electrophilic carbon. The halogen also serves as an excellent leaving group. So moving forward, as far as the reactions are concerned, these are some of the main properties that we'll take advantage of. First, talk about the and then we'll move into the mechanisms by molecular substitution and unimolecular substitution. And we'll then mention factors which influence these mechanisms. And then we'll move on to talk about elimination reactions. Now, as far as nomenclature is concerned, the name of the haloalkane, similar to alkanes, where we choose the longest carbon chain, even if the halogen is not present on that carbon chain, and then of course use the lowest numbers possible. So for example, herein you can see that we have a membered species, that's butane, and there's a chlorine on two, so it's a 2-chlorobutane. In this case here, you can see that the longest chain is, of course, it's a heptane, and you can see that there's a fluorine on the ethyl that's present on the carbon 4, hence 4,2-fluoroethylheptane. Herein, you can also note that we have a 9-member chain. So this is a nonane, and it's decorated with a bromine and 5, and so on. We encounter common names. And for example, on the left here, we have an isobutyl. We came across this when we talked about the alkanes. And there is a bromine present on this isobutyl, so it's an isobutyl bromide. See here, for example, and we have the tert butyl bromide. There are classifications of the type of carbon we're dealing with. So herein, you can see that we have a primary halide, where the halogen is present on the carbon with there's just one carbon group attached to it, or one alkyl group attached. Here, this carbon has 2 alkyl groups attached to it. Carbon with the halogen on it has 3 alkyl groups attached, so this is a tertiary halide. We also have this classification where if there's 2 halogens on one carbon, then that's of course a geminal carbon. It's a geminal dibromide. If they're on carbons adjacent to each other, then we say that they're vicinal. And so we have here a vicinal dichloride. Physical properties, we can now talk about the bond length and the bond strength, and we can look at boiling points and melting points. We got to remember that the alkyl halides are weakly polar because of the rather polar carbon-halogen bond. The electronegative compound, the electronegative halogen realizes the carbon which is electrophilic. And as you can see, fluorine being the most electronegative of this group will therefore have the greatest polarity in its bond. And as you can see, therefore, as you move down the group, you can see because of the size of the species, then of course, strength and will increase. As far as branching is concerned and the size of the group, well, note that as we increase, as we increase the molecules, then of course there is an increase in the board. However, as we increase branching, note, as we increase branching, you can see that there is a decrease in the boiling point. Remind ourselves of what the impact is when you branch and what impact does it have in the melting points. And if you look back on your alkane chemistry, and so consult the alkane lecture, that the branching realizes a more spherical molecule and their better lattice, so better packing, and so better melting. So now to move on to the chemical properties. And the main thrust here is that substitution or elimination. Substitution occurs readily and it competes with elimination reaction. So the two main ingredients for substitution reaction is we need a nucleophile and the halide, the good leaving group would be itself. Of elimination, then we need a powerful base and again an electrophile with a mind yourself that alkyl halides are electrophilic in substitution reactions. So the reagent that is seeking the positive center is called a nucleophile, and it has an unshared pair of electrons. And these would be examples of a nucleophile. So we're talking about a significant lone pair in this case. And we're looking at these lone pairs here attacking our center. So for example, here we have our electrophile, and our electrophile has an electrophilic center. The electrophilic center is what the nucleophile center is going to attack. So a nucleophile has a nucleophilic center which will attack our electrophilic center. These are rather good leaving groups in addition to, so we have the tosylates and we have the mesylates. The tosylates are very, very popular in synthetic chemistry because the leaving itself, you can see, is a very stable conjugate base, i.e. it is the impetus for it to leave. Halogens, of course, are part of this, and you can see that also water, ammonia, neutral leaving groups. So let's talk about substitution reactions. There's two types. There is an SN2 reaction, which is bimolecular, and with this reaction, we pass through a significant transition state. On the other hand, with the unimolecular, we pass through at least one significant intermediate. This is the SN1 reaction. And let's first look at the bimolecular. Here you can see we have sodium hydroxide, which is just reacting with an alkyl halide to form an alcohol, sodium halide as a byproduct. So, for example, we could have the bromide reacting with sodium hydroxide, and the result is methanol. Note that there is a rate associated with this. So the rate is dependent on both the concentration of the substrate and the reagent, which is in this case the nucleophile. So both the alkyl halide and the nucleophile. Hence, because it is dependent on these two concentrations, it is bimolecular. So as we increase the concentration of the alkyl halide, the rate will increase. As we increase the concentration of the nucleophile, the rate will increase. In case of the SN1, which is unimolecular, then again we have, in this case, you can see we have a tertiary alkyl halide. And we realize, in this case, terbutanol, and again, the halide byproduct. Note that the rate in this case is only dependent on halide. So as we increase the concentration of the nucleophile, there will be no change in the rate of the reaction. But if we do the concentration of the alkyl halide, then you can see there will be an increase in the rate of the reaction. The same goes with E1 and E2 reactions as well. Rate dependency. So the speed of the reactions depends on both concentrations in the bimolecular species, but in the unimolecular species, it only substrate concentration and independent of the So herein we're looking at the SN2 reaction. It is a one-step transition state. So it's a one-step reaction going by a significant transition state. We follow second-order kinetics, i.e. rate equals to both the concentration of the alkyl halide and that of the nucleophile times the rate constant. And R that the methyl halide is as this, while the alkyl halide, which is tertiary, you've got a tertiary carbon to tertiary alkyl halide, never undergoes, or very rarely undergoes, a bimolecular event. The resulting stereochemistry also is important to us. There's an inversion of configuration at a stereogenic center. If we look at this mechanism, here we got the hydroxide with an alkyl halide. So the alkyl halide itself is the electrophile, and so we identify the electrophilic center here, this carbon side is our nucleophile, and the oxygen of that nucleophile is the nucleophilic center. And so therefore the nucleophilic center will attack the electrophilic center. So that oxygen, that lone pair on the oxygen, will attack your electrophile, the carbon bearing the leaving group itself has to leave. And so therefore this bond, which is being formed, simultaneously this bond, the carbon halide bond, is breaking. And so therefore end up with a transition state which shows you bond making and bond breaking. We use this garlic cross to tell the reader that we have a transition state. Once the transition state crashes to give us our product, then you will note that there is an inversion of the stereogenic center if there is one present. And here is our leaving group. So in the transition state, we saw where the OC bond was being formed and the CBr being broken, and the result is a new carbon-oxygen bond or carbon nucleophile bond, and we release our leaving group. Reaction is, of course, second-order kinetics, and if we do a plot of the concentration versus the rate, you can see we end up with a linear system. Same thing with a plot of the nucleophile versus the rate. It's also linear, tells you that both are linear. So it is second order, i.e. bimolecular. If you look at the energy diagram, then you can see that we pass through from the reactors, we pass through this transition state, and then we collapse to give us our product. This is terribly important because this is our activation energy. Activation energy. It is exothermic and exogenic. So therefore it's a thermodynamically favorable process. Now note, if we compare a primary alkyl halide versus a tertiary alkyl halide, you can see that in the primary alkyl halide, then there is a lot more access of the nucleophile to the carbon center versus a tertiary alkyl halide where there is very little access. And so the activation energy for the tertiary, the more substituted alkyl halide, is very high, and so the rate is minuscule compared to, say, when you have an access to the carbon center, and so you can see the difference in rate. So we could ask a question, that pertains to this, such as which one is faster, and you would note that methyl halides will be much faster than secondary halides. So we could ask a question like this: which electrophile will react faster in an SN2 mechanism? Set ease of access. And if you notice here, the ethyl bromide is a primary halide versus the cyclohexabromide, which is a secondary halide, etc. So this fella here will be the fastest. SN2. Yes, we could have looked at the benzyl tosylate. We'll talk later. But the benzene ring, or this phenol species, is much bulkier than. So we move on and we'll talk about vinyl species, these era species, and so on. Note, if we have a vinyl halide, this is an sp2 carbon, and the SN2 reaction or SN1 reaction, here these alkyl halides, sp3 carbon. This is an sp2 carbon. The bond is too strong, the carbon halide bond is too strong for dissociation. The same thing here with this aryl halide. That's an sp2 carbon. And the same thing here with alkyl halide, because that's an sp carbon. So in all these cases, working with a normal nucleophile work. Let's look at the reaction in more detail, especially that concerning stereochemistry. If we look closely, we have again our electrophilic center and oxygen, which is our nucleophilic center in a long period. And we end up with our version. So in this case here, stereochemistry, see that this fella is assigned an R configuration. So with inversion, we realize this. Herein, for example, we got a ring which has an halide on it. We're reacting with a methoxide. The methoxide has to attack on the opposite side of the ring. So in this case, the way it is shown, the iodide, is below the ring, and so attacking the iodide would be above the ring. Oxy group trans to the methyl, which was cis, to the iodide that we started with. Could ask for this sort of mechanism, and you can see here another inversion. Here, this is quite interesting because if I deprotonate this alcohol, I realize this species here, and you note that we have a nucleophilic oxygen and an electrophilic carbon in the same molecule. So what we do have is an intermolecular SN2 reaction, which results in a ring. And when we look at ethers later in the work, so molecular SN2. In the meantime, why don't we go ahead and try to answer this question. So pause and work on this one, and then it's below. The starting material that we need will be a species, because it is SN2, it will be a species that has the halide opposite to this hydroxy group. And so therefore, your answer should be, you're absolutely right, D. With that, we're going to move on now to SN1 reactions. And the main features of SN1 reactions, it definitely goes through 2 or more steps, i.e. we're going through a significant intermediate. It is of first order kinetics, so rate is only dependent on the concentration of the alkyl halide. Here we see that the tertiary alkyl halide is faster than the methyl halide, our primary alkyl halide, never undergoes SN1 reaction. As far as stereochemistry is concerned, we go through this trigonoplanar intermediate, and so our product, or products, I should say, reaction, end up being a racemization at the chiral center. Let's have a look at the mechanism. So we're going to look at the reaction of tert-butyl bromide with the hydroxide. Yeah, we know it is going to be SN1 because it is a tertiary carbon, tertiary alkyl halide. Yeah, we know it is first order, i.e. molecular. To be a stepwise mechanism, and we got to get through an intermediate. So the first thing you got to realize that the dissociation of the leaving group, the slowest of the step. So that first step to get to your intermediate, so we pass through this transition state, to get to this intermediate, this first step is the most important. So this step here, yeah, by this height of this transition state, yeah, is the rate determinant step. This fellow is very small. Note, association to realize our intermediate. Intermediate will then be attacked by our electrophilic carbon, which is a carbocation, will now be the nucleophile. So as I stated before, this ray here, because it's so small, because the height is so small, then it's a lot faster, so it's not significant. What's important is the slow step, i.e. this high activation, which is a rate determinant step. So we can look at a set of carbocations, and this is quite informative because, note, the tertiary butyl carbocation, which is tertiary, is very, very stable, and so this will give you the fastest SN1 reaction, while this is very unstable, so the likelihood of this forming is quite low. Slowest reaction. Benzyl and allylic species also undergo rapid rates. And the question is why? The reason why, of course, is that this association will realize a species that we can stabilize via resonance, or that is stabilized by resonance. This question. Immediately, we realize that A would not be suitable because that is an sp2 carbon. Everything else are sp3 carbons. However, we have a tert-butyl, which is quite nice. We have an allyl, which is very nice. Benzyl, which is quite nice. But herein, you can see that if we remove this bromine, if we dissociate bromine, then we end up with a carbocation, which is stabilized by this ring. And so our answer there is E, the terribly stable species. Let's look at the stereochemistries, because as we're looking here at this compound, this association of this compound, in this case we have a compound which has this configuration, realizes a trigonoplanar central carbon. The nucleophile itself, the incoming nucleophile, can attack electron deficient carbon above or below the ring. So if we attach above the ring, then we retain our configuration as, but of course there's a 50% chance that we can attack below the ring, or equal percentage that we can attack below the ring, and so of course we end up with a 50-50 mixture of the R and S, and so our species will therefore be race-mate. The factors that affect the SM1 and SM1 and SM2 reactions, of course, the structure of the substrate, as we mentioned before, concentration and reactivity of the nucleophile. This is for the reactivity of the nucleophile, of course, is for the SM2 reactions only, and the effect of the solvent and the nature of the leaving group. So if we look at the concentration of the nucleophile for SN1 reaction, we state that it's not important to us. Appear in the rate determining step. So we only depend on the concentration and identity of the alkyl halide. For SN2 reactions, remind yourself that it is bimolecular, and so it depends on the concentration of the nucleophile. Strong nucleophiles favor SN2 mechanisms. So herein we have a charged nucleophile that will be very, very, very powerful. This reaction will be much faster than this methanol, which is similar to the methoxide, but it's a neutral nucleophile. So it's much weaker, slower reaction. This is a poor. See if anyone can answer this question. You should have noted that the methoxide is your correct answer because, yes, water is neutral, methanol is neutral, and oxide, acetate, and hydroxide is they are charged. But the acetate, the charge, remind yourself, is being shared between two oxygens. So therefore it leaves us with the methoxide and hydroxide. And of course the methoxide is a stronger base. As solvents are concerned, there's classifications that we got to look at. We have polar solvents that are protic. And these include the alcohols, even organic acids. Note that the protic environment means that we have a labile proton, a hydrogen that is easily removed. So we need polar salt. But in the case of the SN2, we need an aprotic species. So if you note here, none of these cases, DMSO, DMF, THF, acetone, acid nitrite, there are no labile protons. There are no protons where I can remove to form a stable conjugate base. And so these are aprotic. The protic solvents are favored by SN1 reactions, while aprotic solvents are preferred SN2 reactions. Why is that in SN1 reactions, stabilize the carbocation and the leaving group, and this will favor the polar and of course the protons here, the proton end will stabilize the leaving group. On the other hand, in SN2 reactions, we need a nucleophile. And if we solvate our nucleophile, then the attack of our nucleophile will be diminished, surrounded by protons. So in this case here, we have a bromine surrounded by, this will make it very inefficient. Or you could think of it as a bromide leaving group surrounded by very stabilized species. So we could ask a question like this. Again, note that the dimethyl sulfoxide is an aprotic solvent similar to HMPA, but this is a charged nucleophile compared to a neutral nucleophile, and so this fellow here will be this. Let's look at the nature of the leaving group because they are both important to us. The better the species at stabilizing the negative charge of that leaving group, the better it is in both an SN1 or SN2 reaction. Here in an SN1 reaction, you can see that stabilize that species, then it will be much faster. In the case of the SN2, again, it would be great if you could stabilize that species. So the better the leaving group, the faster the reaction. Rather good leaving groups are like toluene sulfonic acids, for example. Oscillates. And of course, you can see that fluorine are these hydroxide and alkoxide. And do not make the mistake of removing these because they do not spontaneously leave to have conditions for them to leave. Molecular mechanism. Note the speed of iodide compared to fluoride. So a question like this would be quite easily answered because we already mentioned how faster the tosylate is as a leaving group. So it's either A or E. Yes, in this case here, we have a primary alkyl halide versus a secondary, primary tosylate versus secondary tosylate. And so therefore, this is faster. A note of warning. Not write SN2 reactions which shows hydroxide ions, alkoxides, or strong bases such as amides serving as leaving groups. So let's review the nature of the alkyl halide. We know that with the primary alkyl, great for SN2 reactions. So we need a good nucleophile, good leaving group. So need polar aprotic solvent. With the tertiary, of course, the nature of the nucleophile is not as important, but basic nucleophile, the stronger nucleophile, the leaving group is It's terribly important. The better the leaving group, the faster the reaction, of course, similar to an SN2 reaction. Solvent has to be polar A and protic. Not have to be, but then of course a secondary halide would fall somewhere in between. Here we're talking about elimination reactions. And there are two types of elimination reactions that will concern us this lecture, and that is the E2 reaction, which is bimolecular. And similar to the SN2, we pass through a significant transition state. And there is also the E1, which is unimolecular. And herein, we have at least two steps where we pass through a significant intermediate. The mechanism for the E2 be, as I stated, it's a one-step reaction going through this transition state, but it's also what we call, it occurs with a periplanar chemistries. And the kinetics is second order, i.e. depending on both the substrate and the nucleophile. As far as regiochemistry is concerned, which is what the resulting geometry will be, we'll notice that small bases will realize the Zaitsev. But remember, we're competing with nucleophilicity, i.e. Can get the substituted product with a smaller base. With a large sterically hindered base, then we end up with the Hoffman species, i.e. we're talking about the production of alkenes, yes? And the substitution product is less likely to compete with these large bases of poor nucleophiles. The reaction of the E2 is anti-periplanar. So herein, you can see that we have here a very strong base, and the substitution reaction is poor. Elimination dominates. The elimination, you can see, has this mechanism where we're attacking the alpha proton. So this is the carbon, the alpha carbon has this hydrogen attached to it, so that's the alpha proton. And so this pair of electron will now move into the space of the carbon in a double bond, and simultaneously we have a leaving an attack on this realize an alkene with these byproducts. It is competing against a substitution reaction. In the case of the methoxide, then of course the substitution product would dominate. The reaction, of course, we stated is one step, anti-periplanar, one plane, and we'll show you this in a few slides. But you can see we have this new carbon-carbon. So look, in the transition state, we have a bond formed between the base and the proton. There's a bond being broken, a bond being formed, and the bond end up with a new an alkene. Look at the kinetics, similar to the SN2 mechanism. We pass through one significant transition states. And of course, that delta G and it's determined by both base and that of the alkyl halide, hence the second order overall. In contrast, the E1 reaction goes through two or more steps, so therefore we go through an intermediate, and it is prone to rearrangement. We'll take a note of this in a few slides. It's first order kinetics, and of course the identity of the R group realized that the alkyl halide undergoes SME1 fastest will be the tertiary. The stereochemistry of the racemization at the Kairos center, that is similar to the SN1. So if we look closely at, for example, we have here a beta chloride. The rate determining step where we have dissociation of the leaving group is a carboxy target, which then attacks then gets attacked by the nucleophile, and subsequently, we can end up with a substitution product, or if it acts as a base, we end up with an elimination product. The mechanism looks like this. Dissociation to give the carboxy target. This is, of course, the rate determining step, and then attack of the base, in this case water, on the alpha proton to realize your alkene. So this is your carboxyl intermediate, and after the attack, realize your alkene. The reaction diagram, you can see, has this high activation energy, which is a rate determining step that gives you your intermediate, and then of course here you have a very fast, a very short gap here between the second transition state, and so this is the fast part of the reaction, and so that's insignificant to us, and we end up with. So note, in this case we have one intermediate transition state associated with it. So if we start to probe synthesis of the alkenes, via these elimination reactions, we note we've already talked about E2 or E1, but we got to think about other variables, such as the stabilization of the alkenes. In this case, hyperconjugation. We got to think about the Zaitsev versus the Hoffman, which we touched on earlier. And then we got to think about the stereochemistry of the E2 reaction and mechanisms of the E1. The halogenation reactions is a source of alkenes, and we can also dehydrate alcohols to generate alkenes. Stability of the alkenes produced determine the speed of the reaction. So the tetrasubstituted alkene alkyl groups is much more stable than a monosubstituted alkene, and a trans alkene stable than a cis alkene. Heterosubstitution, of course, is stability is due to hyperconjugation. Let's look at the mechanism of the Hofmann versus the Zaitsev. There are two types of protons that we have. We have proton A, yeah, and we have proton B. If we eliminate proton A, we end up with an alkene with 1, 2, 3 groups surrounding it. If we eliminate HB, end up with an alkene with only 2 groups surrounding it. Therefore, HA will dominate because with a normal base, because this will give substitute alkene. This is Zaitsev's rule. We will look at examples of where we will end up with a Hofmann. So in this case here, you can see that Zaitsev is a more substituted alkene, and so elimination here of this HA will occur more readily using sodium ethoxide. This is the less steric base. So here 91% is the more substituted alkene. 1, 2, 3. Tri-substituted alkene. If we use a larger base, a much larger base, in this case we're using terp-ethoxide, virtually alkene formed is the Hofmann species. The Hofmann, the least substituted alkene. So, bulky base, small base. Zaitsev. So this is the this is the Hofmann, and this is your anti-periplanar mechanism. Apparent when we use the cyclohexyl ring. And note, we have to have elimination to take place. We've shown that we have to have carbon hydrogen on the alpha carbon and the carbon halide. They have to be axial, and they also have to be in the same plane. Hence, anti and periplanar. Because if you look at this, when the halide is equatorial, at no time do you have a proton in the same plane. So this is elimination in this conformer is not possible. Here, elimination via E2 is possible. We also note that the leaving group has to be anti and not syn. So, for example, if we look at this compound and taking place, we probe by using the chair form of the cyclohexane ring. Remind yourself that the carbon halide has to be axial. So if you look at the alpha protons here and here, there's only one alpha proton that is axial. And so elimination will take place here, not at this equatorial hydrogen. So when we do the attack, then of course it occurs across this plane. This results in this compound. And it's fortunate enough that this is we end up with a 1, 2, 3 substituted, which is, in this case, substituted alkene. Possibilities when you have 2 axial protons possible. And you'll note that if we have elimination with HA, then of course we end up with a Zaitsev, and HB we end up with the less substituted species, and so therefore elimination of A would dominate. Look at this compound, the alkyl halide and the E5, which are both large groups. So this is the more stable conformer. However, elimination is not possible unless this alkyl halide is axial. So the conformer where the alkyl halide is axial, carbon chloride is axial, is the least stable conformer, noted by short equilibrium diagram here. Elimination can occur across this carbon, so this carbon double bond. But because it's elimination across the least stable conformer, then this reaction is slow. So not only do we get the disubstituted species, but we also have a slow reaction. Yes. Ask which of the labor protons in A is readily abstracted? Well, we have this HA, which is not going to be abstracted because it's nowhere close to the alkyl halide. HB is not in the same plane as the bromide. HC and HE are. However, if we eliminate HE, you would realize a disubstituted alkene, while eliminate across here, we have a disubstituted alkene within the ring. So, yeah, and that will give you a disubstituted alkene here in the ring. Up with a species that is substituted. And so HD would be our eliminated. Try to do the elimination mechanism and show us your. We will look at 1 and SN1 reactions as far as carbon-cation stability is occurred. So if we look at the E1 and SN1 reactions, we know that once we have unimolecular dissociation of the halide, we realize a carbon-cation. If there's a possibility of a rearrangement to give a more stable carbon-cation, then we will end up with that rearrangement taking place. So herein, you can see that rearrangement from a secondary to a more stable tertiary carbon-cation via what we call a 1,2 hydride shift, realize an SN1 product that is different from the expected species, and an E one product that is different from the expected species. If we probe this reaction by using this alkyl halide, we will know that once this association occurs to give us our carboxylic cation, then we have a 1,2 hydride shift where the electron between the carbon and hydrogen, the electron pair between this carbon and hydrogen, will move to in here, attack that carboxylic cation, and in this and at the same time takes this hydrogen with it. The incentive or the drive of this reaction is that we moved from a secondary carboxylic cation, a carboxylic cation with two groups of a more stable carboxylic cation. The result is that we can now attack to give us our major product. Another example is here. You can see that association realizes this carboxylic cation. Elimination will give you a here will give you a hydride shift can occur from here to here, and so we end up with a tertiary carboxylic cation, and elimination gives us a heterosubstituted species. These are the type of shifts, hydride shifts, that will occur if there's a possibility. So we can go from a primary carboxylic cation to a secondary. Here we have a primary to a tertiary. Here we have a secondary to a tertiary. And here, this is interesting because both are secondary carboxylic cations. That's a secondary, and that's a secondary. However, you will note that this secondary carboxylic cation is allylic, which this is not. This secondary carboxylic cation is stabilized by resonance, so rearrangement will occur in this case. Typical mechanism, for example, you can see here have solvolysis of an alkyl halide, meaning that the solvent itself will act as realizes a secondary species, and herein we see a alkyl shift. This is a 1,2 methyl shift, so the pair of electrons here following the carbon moves into this space, and now we went from a secondary to a tertiary carboxylic cation, and that's where our attack occurs. To summarize, note that a methyl halide will undergo very fast SN2, the SN2, and of course tertiary will be favorable system, and so we'll be favoring the SN1 and the E1. Both the elimination reactions we need will prefer to have strong bases, but in the bimolecular event, we prefer to have aprotic systems, and in the case of the unimolecular event, favor protic solvents and stronger bases in elimination, weaker bases substitution. And so we end here. Next, I would consult the chemistry, and in this case, the alkene chemistry, expand upon the property of the alkenes that we generate it. Now looking at alkenes the next time. Chat. Leave your likes and comments, and of course, don't forget to share and subscribe.